Yeah, hi there. In this tutorial, we are going to continue with exploratory data analysis in Python. So today we are going to take a data set related to the cancer survival data set, Haberman cancer survival data set. So this data set basically contains data based on the study that was conducted between 1958 and 1970 at the University of Chicago's Billing Hospital on the survival of patients who had undergone surgery for the breast cancer. So the source of dataset is mentioned in the notebook. So dataset contains around 306 data points and it has four attributes, three of which are features and one is the class variable. So the feature variables are age, which is the age of the patient, the time of operation, operation year, which represents when the patient had undergone for the operation, and the number of positive axillary nodes detected. And the fourth is the class attribute, which is the survival status. So it has a value 1 or 2. 1 means the patient survived 5 years or longer after the operation, and 2 means the patient died within a period of 5 years after the operation. So the objective is to classify the survival status of a patient based on the given features. So to start with, we will be importing the libraries NumPy, Pandas, Matplotlib, PyPlot, SPLT, Cbon, and we are going to load the data set which is in a CSV file. And let's have a quick look at the data set for first five records. So we have age of the patient, year when the patient was operated, number of nodes of auxiliary nodes, and the status 1 or 2. Now we'll be doing some transformation. So since survival status 1 indicates a patient who survived 5 years or more, whereas 2 indicates a patient who did not survive for at least 5 years. So what we can do, we can transform it from 1 into 2. Instead of 1 into, we can transform it into yes and no. Yes means the patient survived for 5 years or more longer period, and no means the patient did not survive at least 5 years. So let's transform this status column as following. So I'm just using the map function, and I'm mapping 1 to yes and 2 to no, and storing it back in the df status column, and then converting that particular column into a categorical column. Now year is actually the year 1900 year. So and in the data set that we got was only 2-digit year. So I'm converting it into 4 digits. So basically adding 1900 to whatever the year is already given in the data set. So that is how our data set looks like. Now this looks more complete. Age of the patient, year when the operation happened, number of nodes detected, and the status yes or no, indicating the patient survived for at least 5 years or more. No means the patient did not survive at least 5 years. So we can quickly check at the data type. Age is integer, year is integer, nodes is integer, and status is category. So this is fine. Let's check the data points shape. That's the dimension. So 306 are the number of rows, and 4 is the number of columns, where 3 are the input variables. One is the class attribute, or the dependent variable, we can say. Let's quickly check what is the distribution between yes and no class status. So we can say df dot status, and using value counts you can find out, okay, 225 patients survived 5 years or more, whereas 81 did not survive. If we convert it into percentage, so we have 73% for yes, 26% for no. So we can say that this is an imbalanced classification. Of 73% data points belong to one class, whereas only around 27% data points belong to the other class. Let's check for the completeness of our data set. So we can use df dot is null dot sum. So it will count the number of any null present in a column and just sum it up. So we are getting 0. It means there is no null value present in any of the columns. So data is perfectly clean. So there is no missing data. Let's do the univariate analysis, starting with the age of the patient. So we can use the describe function, and if we describe it, we see that the average age, which is mean age of the patient, is around 52 years, and the minimum age of the patient recorded was 30 years, and the maximum was 83 years, and 75% of the patients were within 60 years of age. Now let's create two another data frames. One is for survived underscore df, which indicates which contains the records of the patients who actually have status as yes, and the other one is not survived data frame, which have status as no. And what I'm doing now in this, I'm doing a one-dimensional plot of the age variable. Basically, what it does is it plots all the data points along the x-axis and keeping y-axis as 0. If I just plot it, we see that there are data points which are overlapped throughout the x-axis. So what it means that based on the age, we cannot distinguish whether the patient survived or not. So let's take it to further and create a swarm plot. So using sns.catplot, and on the x-axis we have the status and the y-axis we have the age, and I'm using kind equals to swarm, use the status, and order is yes and no, and using a data frame df. So if you see, these are the these are the data points related to the patients who survived, and these are the ones for which who did not survive. So if you see, the distribution is more or less similar between those who survived and not survived in terms of the age. However, if you see, there are few data points which are present here but not here. It means the patient which are of lesser age had more chances of survival. That is, if they were close to 30, 31, 32, up to like here, like they, we did not have any failure. So we did not have any, no for the status. Now let's create the histogram for the age variable. So this is the this is created using sns.dispplot, and we see majority of the patients are around 75 years of around 75% were in the age group of 40 to 65 age group. Yes, it's a 40 to 65 years. So now we can plot the histogram based on the survival status. So again, using sns.facetgrid, and data is df, hues the status. So basically it should be colored based on the status, and setting the order yes is for blue and no is for red. We can see there is a lot of overlap between these two histograms. So the one thing that we notice that there is some sort of space here. It means the patients who are of lesser in the age, they had more chances of survival. Next, what I am doing is I'm just creating two histograms in the side by side charts, and just plotting it to just see the distribution. So if you see, for this for this age group bin, uh, its frequency is high compared to those who did not survive. So it means, other than that, there is a lot of overlap. So this is the one thing that we can derive, that okay, less age patient had more chances of survival, at least 5 years or more. So this is what we conclude. There's a lot of overlap in the age group between the patients who survived or not. In the age group of 30 to 40, we notice that the survival status yes has a high probability. So that's the age group I'm talking about, 30 to 40. Now, if I do the same thing via the box plot, so this is the box plot. Yes indicates a patient who survived at least 5 years, and Y, and this one no indicates a patient who did not survive at least 5 years. And if we see the distribution, the median age is more or less the same. And however, if you compare the 25th percentile and um, whiskers, we notice that the patients whose age was less than had who less had better chances of survival compared to the patient with the aged with more age. So let's what I'm doing here is I'm creating a PDF and CDF, which is a probability density function and cumulative density function. So basically, first I'm using np.histogram, creating the hist and the edges. If we sum it up, we'll get PDF. So basically, dividing each of this hist by total of hist. What I'll get is the PDF, and if I use the nb dot cumulative sum function, I'll get the cumulative sum, which is the cumulative density function. Then I'm plotting it both PDF and CDF, and if we see, this is what we get for the two charts. This is for those patients who survived, and this is for those patients who did not survive. The data points are of those patients who survived, 80% were up to age of 62. So if you see, if I go here, this is 80%, and this is what, 62. So 60, so 80% of the patients who survived were within the range of 62 years, and similarly, of the patients who did not survive, 80% were below the age of 62 kind of. So there is a huge overlap in terms of the age. So definitely, again, we come to the same conclusion: based on the age, we cannot distinguish the patient will survive or not. Um, okay, let's take another feature, which is the year when the patient was operated. So if I see, the minimum year is 1958 and 1969. So the data points, based on the data points that we have, these basically are the operations which were conducted between 1958 and 1969. So let's see what is the year-wise count of patients who got operated. So this is what we have, the distribution of the number of patients who were operated in each year. So 1958 has the highest number of patients who were operated, followed by 64, 63, 65, more or less similar. So we had around more than 25 cases in each of the years. If you see, in the last two ones have a smaller height of these bars, so it means very less number of patients are operated in these 2 years, 68 and 69. So let's visualize by year of operation basis how many patients survived. So what I'm doing is, I'm just grouping the data frame based on the year and the status, finding out the count, and I'm doing the reset of index so that everything should come in the columnar format, and just renaming the columns as year, status, and count, and displaying the first four records. So we see for the year 1958, number of patients who did not survive was 12. Number of patients who survived in that year was 24. So in this way, we got this data frame. Now again, I'm just creating a stacked bar chart where, so earlier we had created a simple bar chart. In now what we are doing is, we are just stacking it, in a sense that we are breaking each bar into the number of patients who survived and did not survive, so that we can see on which year we had, I mean, based on the year when the patient was operated, we had more number of survival cases. So if we see, in 1965 year has high percentage of not survived. So this year we had a big number of cases who did not survive in that particular year. Otherwise, in almost all of the years, we had a high percentage of patients who had survived at least 5 years. So let's create a swarm plot. On the x-axis we have the status, and on the y-axis we have the year. If you see, these are the individual data points. Each data point represent, the blue one represents the patient survived, and the red one represents the patient did not survive. If you come here to the 1965 year, if you see more number of data points compared to rest of the year, so it means in that particular year, there was increase in the, I mean, in that particular year, if the patient was operated, there was increase in the number of patients who did not survive. Okay, now let's take the another one, which is the positive auxiliary nodes. So if I see the description of it, so minimum value is 0, and the maximum value is 52, and 75% data is within the four nodes. So it means that there is definitely an outlier here, 52, which indicates as 90% of the 75% of the data has only up to four nodes. So if I just plot it, this is what I'm doing here. Let's plot the percentile value of positive auxiliary nodes. So I'm just plotting, this is the percentile value, and this is the number of positive auxiliary nodes. So if you see up to here, 75 percentage we get only 4, that is within this. But because of this one data point, which is an extreme outlier. Otherwise, if we ignore this one, the maximum value was 30 only. So 85% of the patients who have positive axillary nodes only up to 10. So 85% of patients had not more than 10 nodes. It is very rare to have a patient having more than 30. So having 30 or more, it's very rare, and that's why we have only one data point, which is very rare, and that is an indication of outlier. So again, let's do a one-dimensional plot. I see a lot of overlap between the red and the blue points based on just the number of nodes. Let's move to the swarm plot. If I compare between no and yes, and this is the number of nodes. So those who survived, if you see close to 0 and close to 1, we had a lot of dots related to yes, means the patients who survived at least 5 years. Now let's plot the histogram. And if I see the distribution between yes and no, yes is the blue one and no is the red one. There is somewhat overlap, but we can see the spike at zero, zero number of nodes. So what it basically let's indicate that a lot of patients who had zero auxiliary nodes, they were able to survive. So let's create the PDF and CDF again, following the same logic that we did earlier. We just calculated using histogram. We calculated the hist values and uh, calculated the PDF and CDF, and then we just plotting all, both for individual survived and not survived. So this is what we got. And if we see patients with less number of nodes like 0 or 1, they have high chances of survival. Now let's do the box plot. And if we see for the box plot, though we see patients who had more than 10 nodes also survived. However, majority of the patients who had survived had very less number of nodes, that is less than 5. Now I'm just grouping it on the basis of nodes and the status, calculating the size, and just resetting the index and renaming the columns. We see nodes status counts for 0. The patients who had 0 nodes, so 19 patients actually did not survive, but a huge count of 117 patients survived. So that's a clear-cut indication that if the patient doesn't have that auxiliary nodes, then there is a high chance of patient to actually survive at least 5 years. So again, I'm just creating the stacked bar chart. So which is very clearly visible that for 0, high percentage of people who survived, whereas for the others, for 1 also, if you see percentage of survived patient is high, for 2 is also good. So basically up to 5, 0, 1, 2, 3, 4, 4 or 5 nodes, if a patient has up to 0 to 5, then the chances of survival are more. But as the number of nodes increase, then the chances of survival go down. And yeah, so let's do the bivariate analysis using the pair plot. So I'm just first setting the white grid and doing the pair plot. So for each of the pair of variables, we will get a scatter plot, and for the individual variable, we will get the histogram, kind of a density plot. So for age, there is a lot of overlap. So age is not a good feature to actually distinguish between the patients who survived or not. Year when the operation took place is also not the good feature. Nodes is definitely a good feature, especially for the patients who had lesser, that is 0 or 1 or up to 2 or 3 number of nodes. Now what I'm doing here is I'm using age and the nodes. I'm just plotting it out based on these two and coloring the data points based on the status yes and no. A lot of blue points at 0 indicating these patients who survived. But as we go up, we will see some red points as well, indicating that as the number of nodes increase, there is less chance of survival. And if we actually zoom it, that is, we filter it, especially where the nodes is less than 10, Then we see 0 has all, I mean, for 0 we don't get even a single red dot. So it means all the patients who had 0 nodes, they survived. For 1, there are only couple of cases who did not survive, otherwise most of them survived. For 2 also, 1, 2, 3 data points which did not survive, but others all survived. So up to 2, 3, 3 we have we're seeing some count increasing of non-survival. 4 is also okay. So up to 0 to 4 is the range where we can say patients survived if they have axillary node between, let's say, 0 to 4. And this is a contour plot, what I'm doing between the age and the number of nodes. So this is what we have: a high density. We observe the density of the data points in the age group of 45 to 60, and axillary nodes from 0 to 3. So that is, so if the patient is within 45 to 60 age group and having axillary nodes between 0 to 3, then there is more chances of survival of the patient compared to the other patients. So that is what we are concluding in our this EDA analysis. Thank you.